Okay, good morning. Welcome to I guess this is sort of week 5 and 6. It's part 2 of our energy vocabulary terms. So we'll start with work. And work is a very important aspect of energy because energy is the ability to do work, but a lot of people don't know what work is. The scientific definition of work is when a force causes an object to move. So you push on it and it moves. In other words, work equals force times distance. That's the formula we use. If an object doesn't move, no work has been done. And when you do work on an object, you put energy into it. If I, for example, lift a bowling ball up to the top of the ladder, I've put energy into that bowling ball. If it were to fall, that energy would come back out in the form of kinetic energy. Now, one of the things that makes this a little odd is if you had, say, this picture here where a little girl is picking up a feather and lifting it into the air. She's putting a force on it, and the force is pulling the feather up into the air. She's doing more work than the weightlifter, who he was doing work when he lifted the weights up, but now that he's got them over his head, he's no longer moving them. They're not moving, so therefore he is not doing any more work on those weights. And we can put this into a triangle, a formula triangle. Work equals force times distance. And by changing around the various ways of doing that, we could have force equals work divided by distance. Distance is work divided by force. We can use all those together. Now, of course, some people can do more work at a faster rate than others, and we would say that they do it with more power. A car that can get you from point A to point B in less time is a more powerful car than a car that would take longer. So the formula for power is very simple. It's work divided by time. And since work is force times distance, another way of looking at this would be power is force times distance divided by time. It's measured in watts. I should also mention that work, like energy itself, is measured in joules, but power is measured in watts. And you're probably familiar with different wattage light bulbs. Better wattage gives you more power, more light. Now, the main part of the definitions today is about simple machines. Machines, we usually think of something very complicated, but they are actually a mechanical device that changes the direction or magnitude of a force. So you can't create more work because that'd be like creating energy, which we can't do. But since work is force and distance, by manipulating those two, we can maybe make it easier to do the work. And these 6 machines, these simple machines, are able to do that. The 6 machines are the lever, the pulley, the wheel and axle, the inclined plane, the wedge, and the screw. And more complicated machines, the kind of things that you probably think of when you think of machines, are often combinations of these different simple machines put together. Now, a very important concept in all this is the mechanical advantage. And this is a measure of how much more force you get out from using the simple machine as opposed to what you put in. And usually this comes because you increase the distance, and that reduces the force that you have to put in compared to the force that you get out. And if you get out a greater force, like say you get out twice as much force as what you had to put in, you would say it has a mechanical advantage of 2. So looking at this simple lever here, because we put the fulcrum closer to the load that we're trying to lift up, it's true that I have to push down a greater distance than the heavy object will be lifted up, but I also have to push down with a much smaller force than it would take if I had simply walked over to the object and tried to lift it directly in the air. And in this way, this simple machine has made it easier, maybe even has made it possible for me to do work that I wouldn't have been able to do before if I wasn't capable of producing that force. And you can see how a lever works here by putting the fulcrum, a little triangle thing, closer to the weight that we're trying to lift up. Yes, it's true, he's going to have to push down pretty far to get it to move, but it will push up with a much greater force than it would have otherwise. So let's talk about the lever. Very simple thing. It's a rod, a beam, a rigid stick that pivots on a fixed hinge, which we call the fulcrum. You push down on one end and the other end pushes up. And depending on where you put that fulcrum, it can push up with a greater force than you're having to push down. Now, there's a wide variety of different kinds of levers: the seesaw, the shovel, a tennis racket. Here we see a wheelbarrow, where, think about it, it would be difficult for Emily to actually lift up all these rocks straight up, but by pivoting there on the wheel, it's also using a wheel, she's able to move things around fairly easily. Similarly, with the hedge clippers here, I'm able to chop a stick in half that I could never have hoped to have done if I just was given a knife and told to cut down on it. That wouldn't have worked, but this thing magnifies my strength. I calculated out that it magnifies my strength by 42 times. Makes me 42 times stronger than I would have been if I just had a knife and a stick and I'm trying to push the knife through the stick. Wouldn't happen. But multiply that by 42, I'm Iron Man. The wedge is probably one of the earliest simple machines that was ever made. The first time a caveman took a rock and chipped away and made a sharp edge, they had made a wedge. It's a triangle-shaped object, and what it does is it changes the direction of the force. Now, this one doesn't actually increase the force, but it changes the direction. You're pushing down, and the wedge is pushing to the sides. So look at this illustration here. You're slicing through bread. You're pushing down with the knife, and because of the shape, the triangular shape of the knife, it's pushing the bread slices apart. All knives, all sharp objects work on this premise. A doorstop also works on this premise. The door is pushing to the side of the doorstop, but the doorstop is pushing up and down against the floor and the bottom of the door, and that stops the door from moving. The wheel and axle, of course, was one of the great inventions, and we've already talked about how wheels reduced friction by turning sliding friction into rolling friction. Wheel and axle is a large wheel attached to a smaller one, or a tube, wheel-shaped tube, that we call the axle. So these two will rotate together. The force is transferred from the one to the other. Now, what is the advantage of this? If you look at, here's a simple sketch of a wheel and axle, and you can see that he is turning the larger circular wheel here to get the smaller one to move. And it's fairly easy for him to do this. Now, suppose he didn't have this long handle here to make the large circle. Suppose he tried to just grab the cylinder, the axle, and move it. It would be a whole lot harder. Take the doorknob off of your door and just try to turn the little thing that the doorknob is attached to. Or imagine taking your steering wheel off and trying to turn your car with there's probably like a little axle inside the steering wheel, trying to turn that with your fingers. Absolutely impossible. You could maybe attach some handle to it, but the bigger the steering wheel, the easier it is to turn. So turning the large wheel is easy, and that causes the much harder, smaller wheel to turn. It would take a lot more force to turn that smaller wheel. Now, one of the easiest ones to understand is the inclined plane, which is simply a sloping ramp. And you're trying to go up. Now, you could do this by lifting yourself up through the air, pushing down. That's kind of hard to do. Imagine trying to climb a pole. May or may not be possible. You're having to lift up your entire weight. That's a lot of force. But if you put a spiral staircase around it, okay, you're going a much greater distance than just the distance from the bottom to the top of the pole if you're using a staircase or if you're using a ramp. But you have to use less force. It becomes possible. I can climb up a spiral staircase 5 or 6 stories before I collapse from exhaustion. There's no way I am lifting myself up a pole. I mean, a ladder would be hard enough, but I could probably do that. It's not going to be easy, but at least I don't slide down. The plane makes it much, much easier. Now, once again, though, look at the trade-off you're making. The one on the left would be easier to push the box up. You would not need as much force, but you're having to push that box over a great distance. The one on the right is a much smaller distance, but you're not getting a tremendous advantage there. Pushing that box up is not a whole lot better than just lifting it straight up. And you may not have the ability to push, depending on what's in the box, you may not have the ability to do that. Making the ramp really, really long and sliding it makes it much less force over a greater distance. Again, There's a sacrifice. There always is, one or the other. The screw is an example of one that doesn't necessarily increase your force, but it changes the direction. I could not, with my hand, stab a nail into a board. I would hurt myself. But with a screw, all I have to do is turn it. And I'm turning it a lot. I may have to turn it 20 times to get it to go all the way in. But as I'm turning it in a circle, it's going down. It's changing its force. It's doing what I want it to do, go in the direction that I want in a way that doesn't take as much force as I would need to stab it in. And the last one is a pulley. And a pulley can be something that can either simply change the direction of your force or change the direction of your force and increase the amount of force that you get out. It's a wheel that can spin with a flexible rope cord chain on its rim. And if you use them singly, like in this first example, the only thing you're really getting out of it is that you're pulling down and the load is being pulled up. Now, it's easier to pull down on a rope than to pull up on a rope. When you pull up on a rope, it really depends on your strength. But when you're pulling down, you can use your strength. You can also just use your weight. Use the force of your weight. Grab onto the rope and sit down. And if the load weighs less than you, it'll be pulled up. Not a lot of effort. But the really cool thing is when you take multiple pulleys. So look at the example on the right there. We've got 4 different pulleys, 4 different ropes. And if you set these up correctly, he is pulling up a 200-kilogram object. That might be strong. That might be heavier than he can pull down, but maybe he can pull 50 kilograms, and that's what he's doing. Each one of those ropes is pulling on that 200-kilogram rope, so he's getting a mechanical advantage of 4. Now, notice the sacrifice, though. He's pulling the rope 4 meters, and the object only goes up 1 meter. So again, 4 times as much distance, but only 1/4 as much force. And with enough pulleys set up, you could lift up just about anything within reason. Obviously, there comes a point where it's too heavy for the system to hold. But could you lift up an elephant? Yeah, I say if you had strong enough ropes, strong enough pulleys, and lots and lots of pulleys, you could set it up in a way that you might have to pull that rope 100 feet to make that elephant go up 1 foot, but you still do. So there's our definitions for the week, and we'll talk soon. Okay, bye-bye.